Okay, let's get started. A couple logistics things first. Today is Tuesday, so after class on Tuesdays, I usually hold my office hours back at my office, which is in Farrell Hall. But I found it's useful because most of you have your machines here. If we just go straight upstairs after class, so if you've still got issues with installation or other things to do with PyroSim, I will hold my office hours today right after class upstairs in the CS sitting room, which is right next to the main office there. Everybody know what the number is there? Okay. Upstairs. Sorry?
360, 50 something?
Something like that. Okay. Let's see. So that's office hours. Let's talk a little bit about the assignment. So we're going to talk in a moment about assignment 3. So undergrads, I think everyone submitted assignment 2 by last night. And we'll talk a little bit about assignment 3. Grad students, you're now going to be working on assignments 5 and 6. And you can see I posted them down here for the undergrads. So also for the undergrads, if you want to work ahead, all the assignments are there up to and including assignment 6. Any questions about assignment 2 or any of the assignments? Yep.
On Max, what's the eval time equivalent to 1 second?
In how many time steps do you need to send to eval time to get 1 second? 1 second of, this is where things get tricky, right? So when we're talking about simulation, there's simulation time, wall clock time, which is the amount of CPU time, and then, wall clock time, which is wall clock time. So if you want 1 second of your time, hard to say. It depends on your machine and your platform and so on. So not exactly easy to get it to be.
I only ask because on Windows,
Yep.
it's about 2,500 time steps.
Yep.
And that makes the whole simulation run in a matter of milliseconds. So whatever you want to watch the simulation go
Yep.
of the tube going through the floor, getting pushed up and falling back down, you have to hold Control O. Otherwise, it finishes before you can even see it.
Okay, so this is on Windows machines, right? So that we have figured this out. So on Windows machines, a time step is much faster than it is on a Mac or Linux machine. So I'm pretty sure for all the, so far I've made sure that in all the assignments, it doesn't matter the number of time steps that you run your simulation for. So figure it out for your machine so you get a couple of seconds of wall clock time.
I mean, it'll go for the amount of time in the wall clock.
Yeah.
But the actual, you can't view the simulation.
Because it just goes so quickly.
It goes in a millisecond.
Uh-huh.
And you just get 4.5 seconds of wall clock time
of it just doing nothing. I see. Okay. Have others had that experience on Windows machines? Okay. So I will look into that. There's a way that I can go into the C side and actually try and slow things down. So one time step, the time step corresponds to a shorter period of time in real time, which is probably what we need to do for the Windows machines. Okay, I will look into that today and see if we can come up with a solution. Yes?
I have a question about assignment 5. In assignment 5, that we were asked to post a video.
Yes.
So do you have any advice for recording the screens in Ubuntu?
Okay, let's see. So you're talking about assignment 5. So that's right. So when you get to assignment 5, part 2 of assignment 5 is a random search algorithm. So you're going to start to iterate over variants of your robot. And right at the end, it asks you to capture some video of your robot in action. So you're on Ubuntu. Anybody know how to screen capture video in Ubuntu? No?
There's a good app called Record My Desktop.
Record My Desktop for Linux?
Yep.
Okay, Record My Desktop for Linux.
Software store.
What's that?
It's in the software store.
It's in the software store. Okay. Okay. Failing that, you can just hold up your phone and record the screen. There are no points in this class for video quality, so you don't have to worry about that. However, the easiest way to get some video, that's fine. The one thing that you do need to do when you capture some video is we're going to ask you, actually, why don't I just run it here so you can see what we're looking for. Okay. Haha, okay, let's try the hill climber. Okay, this is assignment 6 where you'll be creating a hill climber which is going to search over variants of your robot. So I'm playing back a bunch of robots, and then in the video we're going to want to see the fitness values of those robots. So make sure that when you record your video, that the video is sufficiently high resolution that we can read these numbers. So what we want to see, for example, in assignment 6 here, is that when a child robot gets a higher fitness than its parent, the child replaces the parent. So when we're assessing assignments 6 and forward, you're going to be trying to capture video of your robot in action and also some running statistics on the side. And myself or the TA are going to be comparing the video with the fitness statistics. And from that, we can infer whether your search algorithm is working correctly or not. So a student did post a solution to the hill climber this morning on Ludobots, and I had a look, and it was the resolution was too low that we couldn't read off the numbers. So I asked that student to resubmit the video. So it doesn't matter to us if you capture video with your phone and your hand is shaking a little bit. None of that matters as long as we can see the robot and fitness values. Okay. Any other questions about assignments? No? Okay, so let's talk about assignment 3 for a moment. Okay, so in assignment 3, you're now going to be adding sensors to your robot. So we've created our pair of objects, the 2 cylinders. We've connected those cylinders together with a joint, and that joint is going to allow our robot to rotate, the 2 cylinders to rotate relative to one another. And now we're going to start to instrument our robot with a few sensors. And at the beginning of the sensors assignment, you're going to be adding to the engineering drawing that you've been developing in assignments 1 and 2. And in assignment 3, you're going to be adding 1, 2, 3, 4 sensors. So we're going to place a touch sensor in the white cylinder, a second touch sensor in the red cylinder. You're going to be adding a proprioceptive sensor. The proprioceptive sensor is going to be attached to the joint, and the proprioceptive sensor is going to report what about the joint? The angle, right? So what is the angle of the current joint? And then finally, you're going to be adding a 4th sensor, the ray sensor. And as the name implies, the ray sensor sends out a ray and reports the distance of that ray. If it's pointing off into the distance, that sensor reports its maximum value, which is 10 units of distance. As the red cylinder starts to rotate down towards the ground, that ray will collide with the ground, and the value reported by that sensor will shrink. Yeah? Okay, so there are lots of other kinds of sensors you can add to your robot, and we'll introduce those in future assignments. But as you can see here, most of the sensors, they're attached to an object, with the exception of the proprioceptive sensor, which is attached to a joint. Okay. On step 23 here, let me zoom in a bit. In step 23 here, you're going to start using an additional Python package called Matlablib. And Matlablib is a very popular Python program that allows you to visualize data. If you've taken my HCI class, you've already seen Matlablib. So again, some of you, depending on your platform, may have some challenges installing Matlablib. If any of you have installed Anaconda, which is the Python, the umbrella Python package, it comes with Matlablib installed. If you just have Python on your machine, you'll probably have to install Matlablib separately. Did you have a question? No? Okay. Okay, so once you do install Matlablib, what you're going to be submitting in assignment 3 is now not screenshots of your robot, but screenshots of the sensor data generated when your robot moves. So here is a screenshot of the touch sensor. And you can see that in my case, I'm running my simulation for 100 time steps. Again, some of you are going to be running your simulation for more or less time steps. Doesn't matter to us how long this horizontal axis is. The vertical axis is reporting the values of that sensor. From what I've told you so far, what sensor is this? And how do you know? So we've got our robot, which is made up of the white cylinder and the red cylinder. And when we start up the simulation, the red cylinder just kind of rotates down and collides with the ground. What sensor do you think we're plotting here?
The touch sensor for the red cylinder?
The touch sensor for the red cylinder, that's correct. And how do you know that?
It starts at 0, so it has no value. So I assume it wouldn't be touching anything.
Absolutely.
And it falls to the ground, hits the ground, and it bounces, I guess, once. So there's one point where it's not touching anything.
That's it. So as you start to develop the sensor part of your robot, you're going to learn how to look at this and sort of understand what the robot is doing and vice versa, right? So we've got our touch sensor in the red cylinder. The red cylinder is not in contact with anything. Remember, we're excluding objects to which it's attached. So yes, it's touching the white cylinder, but we're ignoring that. It starts to rotate down. Touch sensor is reporting 0, 0, 0, 0, 0. And at the 30th time step, the red cylinder collides with the ground. The touch sensor captures that information and starts firing at its maximal value, which is 1. For a little while, the red cylinder happens to bounce back off the ground for a few time steps, and then the red cylinder settles back, touching the ground, right? So in assignment 3, you're going to be submitting a few of these plots, and either myself or the TA are going to be looking at this, and we know what sort of sensor data your sensor should be reporting. Right? Again, if you're running your simulation for much longer than 100 time steps, shouldn't matter, right? The touch sensor the red cylinder will just stay in contact with the ground indefinitely. Okay. The other thing you'll notice in assignment 3 is we ask you to match this screenshot, but towards the end of this assignment, you're going to have to generate some of these plots, and we don't tell you what it should look like. But again, you should know what it's supposed to look like based on the sensor and what the robot is doing, which for the moment is just this, right? Okay. Any questions about assignment 3? Okay. All right then, so back to lecture. We're working our way through the tools of the trade, which is good timing because you're in the process of implementing these. For those of you that have moved on to assignment 4, you're implementing neurons and synapses, which we were talking about last time, and we'll finish our discussion of artificial neural networks today and hopefully get a good way through lecture 5 on evolutionary algorithms. Okay, so back to lecture 4, just to refresh your memory, we started with a very familiar robot, the Bratenberg vehicle. We threw away the body and just kept the brain, or the artificial neural network, where we have 2 sensor neurons and 2 motor neurons, and a sensor neuron is attached to a motor neuron with a synapse. We then introduced this idea that any given neuron can have more than one incoming synapse, and those incoming synapses are influencing the new value of the target neuron. And the heart of most neural networks is multiply the value of the source neuron by the weight of the synapse, and then add to that raw sum the value of the next source neuron, multiply it by that synaptic weight, and compute that raw sum. Once we have that raw sum, once we've computed that raw sum for each of our target neurons, we then usually pass that raw value through an activation function. And there are different kinds of activation functions that are used in different artificial neural networks, but they're all implemented for the same reason, which is to squash the value of the neuron to lie between some desired range. So in the assignments, we're going to be using the tanh function, which ensures that our neuron values will always range between -1 and +1. the reason why we're using the tanh function and we want to squash things between -1 and +1 is that you're going to start to send the values of some of the neurons to the motors, right? And we're going to output to the motors a desired angle for our joint. And in the robot that you're working with right now, we're going to assume that a joint can rotate between +45 degrees and -45 degrees. So we have a range of motion for that joint. So we're going to take the value from the motor neuron, which because of the activation function we know ranges between -1 and +1. And we're going to scale that to lie within the range of -45 to +45. And then we can send that as the desired angle to the joint. If we didn't know what the range of the motor neuron was, it would be hard to scale it to a range of -45 to +45, or whatever the joint required. So it just helps us when we're going to actually use the values arriving at the output layer of the neuron. So far, so good? Okay, so neurons, synapses, synaptic weights, activation functions. Put all that together, and we can now start to construct neural networks that compute a function. They take values arriving at their input, and we can then read off the value arriving at the output and treat that as a mapping or a function. We looked at setting the synaptic weights and the threshold for the single output neuron here to compute the AND function. We then looked at changing the weights and the threshold of the neural network to compute a different mapping, which is the OR function. And this is important because this is, in essence, what you're going to be doing with your robot. So you're going to be building an artificial neural network for your robot, and then you're going to be changing, or the evolutionary algorithm is going to be changing the synaptic weights, which changes the mapping from sensors to motors. So when you're running your hill climber, for example, and you're watching your robot over and over again, and it's doing slightly different things, that robot has exactly the same body. The neural network inside has exactly the same structure. The only difference between one robot and the next is these synaptic weights, which change how the robot moves in response to sensor values. Okay, so here's the simplest example of this. We can change the weights and the threshold for different Boolean functions and an OR. And then we started to look at this network the last time, which introduces another concept, which is hidden neurons or a hidden layer. So we now have our input neurons up here, our output neurons down here, and two neurons in between, which are sort of hidden from the real world. They don't directly experience input from the outside world, and they don't directly send outputs to the real world either. They're hidden in between. And we introduced these two hidden neurons because we realized that there was no way we could set the weights and the threshold for this simpler network to compute the XOR function. Okay, so we've introduced these two hidden neurons, and we started to sketch out a strategy here, which is that these two hidden neurons are going to compute two partial results, and then we're going to combine those partial results into the final output, which should match the XOR function. What are those two partial results, or those two subfunctions that these two hidden neurons should compute?
And an OR.
And an OR. So we're gonna set the weights and threshold of this set over here to compute the AND function. We're going to set the weight and threshold over here to compute the OR function. And then how are we going to combine these results? Why are we computing the AND function and the OR function?
You can subtract the AND from the OR.
Exactly, right? So if we look carefully here, if you look at the first three rows, these first three rows correspond to the OR function, right? So the OR function should flow down to the output 3 out of 4 times. But in the 4th time, we want to try and suppress the output of the OR function, right? We need to recognize that we're now at this AND case when both ones are here. We're computing the and function over here. So this neuron is only going to light up when both inputs are 1. Right? This neuron over here is computing the and function. When we have both zeros or either 1, this thing stays at 0. So when we input 2 1s at the input layer here, this one lights up and it does, what does it do to the output? You mentioned subtraction.
So put a negative weight on it.
Put a negative weight on it, right? So remember we talked about inhibitory synapses last time, and excitatory are the ones that have a positive weight. So here's our weights and our threshold in brackets here. So actually, I've got this the other way around, right? This lower threshold means that this is going to compute the OR function, and the higher threshold over here means this one is going to compute the AND function. So in the case, for example, of this row here, we have 0 and 1. So we have 0.5 arriving at this neuron here. 0.5 is above 0.4. So this neuron is set to 1. What happens over here in this case?
.5 is less than 0.8, so it's 0.
So it's 0, right? So 0 times 0.5 plus 1 times 0.5 is 0.5. That's our raw sum, which is less than the threshold. So this neuron is set to 0. And what do we get at the output layer? We now have 1 here and 0 here. We now need to compute the value at the output layer. One, right? So the value down here, 1 times 1 plus 0 times minus 1 is 1. 1 is greater than the threshold we set here at 0.5. So we get an output of 1, which matches the desired output, and we're all good. Right? You can do this case and this case, and you should get a similar result. Okay, you can do the math on your own here and work this through. In the final case, which is the tricky one, right, we have both inputs set to 1. So we set the values of both input neurons to 1. These flow through. Remember, this one is computing the OR function. So the OR function is set to 1 when both inputs are 1. This neuron is computing the AND function. So 1 times 0.5 plus 1 times 0.5 is 1. 1 is above the threshold of 0.8. So the final value of this neuron is 1. So this neuron over here has recognized this condition where both inputs are 1. And by setting an inhibitory connection here, the AND function suppresses the output of the OR function, and the result down here is 0. Right? So a way of thinking about what this neural network is doing functionally is allowing the OR function to do what it does in 3 out of the 4 cases. And this second hidden neuron is a sentinel. It's watching when the special case occurs. It lights up only when that special case occurs. And when it lights up, it inhibits the behavior of this path in the network. Okay, so again, these are very simple neural networks, and it's going to be very difficult for us to design these by hand. But in these simple cases, we can sort of get an intuition for what neural networks are doing. They're taking their input and producing an output. And sometimes parts of the network are inhibiting other parts, and that allows us in this case to compute a nonlinear function, which is the XOR function. So one of the questions you can start to ask once you have your own evolutionary robotics simulation up and running is, how complicated a neural network do you need in order to evolve your robot to do X? So if all you do is want your robot to run from point A to point B, do you need a nonlinear transformation from sensors to motors? Maybe yes, maybe no. We'll come back to that. Okay, so that's hidden neurons. Again, this is a course about evolutionary robotics. There is the whole branch of machine learning, which is how do you train these neural networks to do something desirable? What happens if you have a learning algorithm? So now we're not setting the weights and the thresholds by hand. Our machine learning algorithm is trying to determine what the weights of the network should be in order to produce some desired output. You can see here I've expanded our neural network a little bit, so now we have 2 input neurons, 2 output neurons, and here's our truth table over here. And let's imagine for one of the rows in this truth table, when the input is 0 and 1, we want the output to be 1 and 0. So we want the output to be 1 and 0 in this case. Let's say at the moment in this neural network, all of the weights are set to 1. In this case, the actual output is 1 and 1. So in this output neuron is doing what it's supposed to be doing. This output neuron is not doing what it's supposed to be doing. So we've localized some error in this case. There's 0 error here, but there is non-zero error here. So what does the machine learning algorithm do next? How does it know how to alter the weights to try and reduce this error? We want our output neurons to output 1 and 0 so that we have 0 error in each case. But we don't. We have 0 error here and non-zero error here.
You defined an error function like cross entropy.
Okay, so we define an error function, and then we take that error function and we propagate backwards from the output layer towards the input layer. So one of the fundamental learning rules in machine learning is this idea of backpropagation. We scan across our output neurons, and for any of them that have a non-zero error, we go backwards along the synapses and we change the weights according to a given error function to reduce that error. So let's actually do that. If we move backwards, we could, for example, choose to set both of these weights to 0. And now, as you can see, we've reduced the error to 0 in that erroneous output neuron. That's the basic intuition behind backpropagation. Again, this isn't a class on neural networks, so we're not going to go into the underlying mathematics, but I think the intuition is kind of clear, right? You're making localized changes to the synaptic weights. We're not changing all of them. We're just changing those that are close to the error. So by doing so, we have a low chance of increasing error for other input patterns. We're not changing everything. We're just trying to change synapses that are close to where the error is occurring, right? So this is like using tweezers on a neural network. Go in and fix things in a particular place. Okay. Another important feature of neural networks, which might crop up in your robotics experiments, is a common problem with neural networks known as overfitting. Overfitting is failing to learn the proper relationship between input and output. So it turns out that with a lot of neural networks, you can train them using backpropagation or other methods, that they will actually produce the output that you want, but perhaps unbeknownst to you, they're producing that output in a way that they shouldn't be. What does this mean? Well, let's have a look at another example here. So again, we're just looking at neural networks that are computing a transformation from their inputs to their outputs. Let's imagine that we have a clinical data set. We have health records from a number of patients, N patients. So each health record for each patient is on a row here. And then for each patient, we've performed some clinical diagnostic, and they're either positive for a given symptom, which is 1, or negative for that particular symptom. And there are k of these symptoms. So we're going to have k input neurons. We would like to try and train a neural network to be able to reproduce the actual state for these patients. Some of these patients are actually suffering from some particular disease and others aren't. So we still have a binary truth table here, but we're looking at this in a clinical domain. Why would we want to do this? Because patient N+1 walks into the hospital. That patient is administered the K tests for these K symptoms. We take the results of those K tests for that new patient, and the neural network will predict, yes, there's a good chance that this patient is suffering from this disease or not. Okay. A lot of practical applications for neural networks. Okay. Let's imagine that in this case we have built our neural network in the following way. We obviously have k input neurons for our patients, and we also have a lot of hidden neurons. Let's imagine that we put too many in, and you'll see what I mean by too many in a moment. Let's imagine that we put in actually n hidden neurons, and each of these n hidden neurons are attached to our single output neuron. And then we apply, again, back propagation or some other learning method so that for all of our n patients, whenever we take the symptoms suffered by that patient and supply them to the input layer and propagate the value down to the output layer, the value that arrives there matches the actual disease state of that patient. So imagine we do this for a while and we finally obtain a neural network that gets 100%. For all of our n patients, it correctly reproduces the actual disease state of that patient. Right? Excellent. We're good to go. We send the neural network to the hospital, and they use it to try and make predictions about disease state of new patients that enter the hospital. Unfortunately, in this example here, the neural network has overfit the data. We're not going to go into what the actual weights are, but you can actually figure out synaptic weights here so that the first the first hidden neuron only lights up, only goes to a value of 1 when it recognizes the symptoms of patient 1, and otherwise the value here is 0. And same thing with the second hidden neuron. This second hidden neuron will only go to 1 when we supply the combination of symptoms for patient 2. Otherwise, this hidden neuron goes to 0, and so on. So similarly to our XOR example, where we had one hidden neuron that was computing the AND function and the other hidden neuron was computing the OR function, here we have n hidden neurons which are recognizing individual patients. What do you think the synaptic weights are down here? We have this hypothetical neural network, which is correctly predicting the disease states of all n patients. We now know that each of the n hidden neurons recognizes each patient. What do the synaptic weights need to be to get this neural network to predict correctly? Did you have an idea?
I think it is 1 for every synapse.
That's right. So we have patient 1 here. So in this case here, we've supplied the symptoms for patient 1. What does the output need to be here?
1.
1, right? Or yes. So what does the weight here have to be? Okay. What about patient 2? So this hidden neuron lights up whenever it recognizes patient 2, and all the other neurons in that case are silent. They're all 0. What does the synaptic weight have to be here?
I think it is.
So we supply all the symptoms for patient 2 at the input layer. The second hidden neuron goes to 1. All the other hidden neurons go to 0. What does the synaptic weight then have to be here?
0.
Not 0. 1. We want, actually, in this case, we want, the disease state for this particular patient is 0. And this is lit up as 1. So what does the synaptic weight have to be here?
Why is it lit up as 1?
Sorry?
Why is it lit up as 1 and not 0?
So we're assuming that this neuron is going to light up when it recognizes patient 2.
Oh.
So patient 2 has symptoms, the case symptoms like this, so we supply those, and this neuron says, I recognize that these are the symptoms for patient 2. But we need this neural network to correctly output no down here for patient 2. So what does the synaptic weight have to be? If the synaptic weight was 1, we have 1 times 1, And we get 1 here, right? That would be an incorrect prediction.
So is it less than 0.5?
That's the threshold. You're thinking about the threshold here, right? So the weight here could be 0 or -1, anything that's low, right? We want sort of this neuron to inhibit the output here because the patient in this case does not have the disease. Right? So we sort of have all of these hidden neurons which are recognizing their respective patient, and then once they turn on, we assume that the machine learning algorithm has trained these synaptic weights so that when the single neuron that's at 1, we multiply it by its weight, it produces the correct output. So if we were to march down the outcome variable here, so 1, 0, 0, we would see 1, 0, 0 here. So overfitting is just another term for memorization, right? The neural network in this case is memorizing the particular combination of symptoms for a given patient and then is memorizing what the actual disease state was for that patient, and it outputs that prediction, right? So you all have a final exam tomorrow morning. You haven't had time to absorb all the material. What's your best thing to do? Go try and find some exams from last year and memorize all the questions on last year's exam, right? Not unlike students, neural networks will often say, I'm not going to bother looking for the underlying pattern in all the questions and answers I've seen so far. I'm just going to memorize them all, right? So assuming that this neural network has enough hidden neurons, it's large enough, it can memorize all of the situations for each of the patients and predict their outcome. Okay, so you've memorized last year's final exam. Tomorrow morning you sit down from the exam, and luckily you see that the professor was lazy and is giving exactly the same exam that he or she gave last year, right? 100%. Great. What do you not want to have happen tomorrow morning? A brand new final exam, right? So if patient N+1 walks into the hospital and patient N+1 has some combination of symptoms that doesn't exist in any of the N patients that the neural network was trained on, how is the neural network going to do at predicting the actual disease state of patient N+1? Who knows? Who knows what it's going to predict, right? It's probably not going to be correct. So this is a very real challenge in machine learning, this idea of overfitting. So instead of predicting disease states of a patient, we have an artificial neural network inside of an autonomous car, and it's been trained on thousands of miles of video footage from the road, and unbeknownst to us, there are some situations that can still occur to that car that doesn't match anything in its experience and is outside its experiences. It may not be able to predict what it should do in that novel situation. Yes?
I just want to know how can you prevent this from happening?
How can you prevent overfitting? That is the million-dollar question. Actually, it's more than $1 million these days. It is a very, very important and unanswered question in artificial neural networks research. So we do know from this example that if the network is too big, we run the risk of overfitting. But we also know, going back to our XOR function here, if the network is too small, it can't predict our outcome, right? So we're always playing this game in neural networks between trying to determine the topology of the network. So how many neurons, how many layers in the network, how many synapses, how are they wired up? What's sort of the size or structure of the network that's neither too small nor too big? Not an easy thing to do in practice.
How can you tell when it's been overfit?
How can you tell when it's been overfit?
It's hard to tell, but you can use a validation set
Okay.
to test on your own data to see if it's overfitting.
Absolutely. So one common method is to use a validation set. So going back to our example now of the clinical data set, We have our n patients over here. Maybe we randomly pull out half of the patients. So now we have n over 2 patients. We set those aside in a validation set, and we train our network on the remaining n over 2 patients. And we keep training them, but we watch to make sure that the error of the predictions on the validation set, those additional n minus 2 patients that we set aside, the error doesn't go up. Right? So if you're doing your math homework and I'm occasionally asking you questions from some other midterm that you haven't seen before, but all you're doing is actually memorizing what you're seeing in the book, your error might actually stay the same or start to go up on the questions that I'm showing you that you haven't seen before.
What's like a common margin of error that's acceptable, or does it depend on each situation?
What's a common margin of error? Again, that's a very difficult problem to answer. Right? What's a margin of error that a hospital staff might tolerate in predictions of a neural network? What margin of error might you allow in an autonomous car that says, no, that's not a child in the street, it's just it's an empty grocery bag? Right? There are very real practical implications of these kinds of questions, and they're not easy to set from a technical point of view. Okay, again, this isn't a class in neural networks. I just wanted to sort of give you a taste for some of the challenges in neural networks, which will come up again when you start to evolve neural networks for your robots. Okay, last concept that I wanted to introduce in relation to artificial neural networks are recurrent connections. So far, in all of the networks that we've been looking at, the arrows, or the synapses, are pointed in one direction, away from the input layer and towards the output layer. So those are forward connections, flowing forward from input towards output. But we can also have recurrent connections, which are either lateral, so they're connected to other neurons in the same layer, or in some cases, they can actually point backwards towards upstream layers. Okay, why do we care about recurrent connections? Because they add memory to our artificial neural network. So if you look at, for example, a purely forward network, or a feed-forward network here, this network can't remember anything that happened to it before. Everything we can determine this output, or the output is only determined by the current input to the network, right? That does everything. Has nothing to do with what the previous values were at the input layer. So any feed-forward network like this has no memory. Whatever it produces at the output layer is 100% determined by whatever is currently at the input layer. Okay. So how does a recurrent connection work? Well, let's have a look, for example, at motor 1 here. So again, we're talking about a neural network that's embedded in a robot. This robot has 2 sensors, and it has 2 motors here. We can see that motor 1 now has 3 incoming connections, one from sensor 1, a second from sensor 2, and a third one from its neighboring motor neuron. So how do we compute the new value of motor 1? Well, we're going to assume that at time step 1, at time step t in this case, we computed the values of the motor neurons. If t equals 0, meaning this is just the first time step that this neural network has ever been updated, we're going to just ignore these recurrent connections for a moment. Now at time step t we're going to ignore these recurrent connections. So at time step t equals 0, just compute your neural network like this for now. Now at time step t plus 1, we're going to compute the new value at motor 1. We can see that the values at the sensor layer have changed from time step t to t plus 1. So we take this value times this weight, plus this value times this weight, times this value times this weight. But at this time step t plus 1, we're only working on motor 1. We haven't even gotten to motor 2 yet. But we need a value here to multiply by the synaptic weight. So which value do we use? The value from the previous time step. And that's where the memory comes in, right? So now, whatever the new value is at motor 1, that new value is a function of what the robot is currently seeing or sensing. and its previous state somehow, right? Whatever the motor was doing in this case at the previous time step. So now we have a robot that can remember a little bit. Now that we've just talked about recurrent connections, I want to go back to assignment 4 for a moment. And in assignment 4, you're going to be actually implementing neurons and synapses. So at the point when we're talking about synapses, I showed you this last time, so let's come back to this formula here. Now this formula should make a little bit more sense to you. Remember that we're using this equation to compute the value of the ith neuron at time step t. And we do so by multiplying all of the incoming neurons, all of the uppercase J incoming neurons to this target neuron. We're multiplying it by the value of those neurons at the previous time step. So we do that so that now it doesn't matter to us whether weight Ji is a recurrent synapse or a forward synapse. Doesn't matter. We're just using the values from the previous time step. This means, however, that if Y sub I is a motor neuron, and Y sub j, or one of the Y sub j happens to be a sensor neuron, we're also just using the sensor value from the previous time step. Doesn't matter too much, just keeps things simple for us. Now when we update the value of a neuron, we're going to multiply the values of all of the source neurons that attach to it by their values from the previous time step. And then again, we're wrapping it in this tanh function. You'll notice that we also have the value of the target neuron here at t minus 1 because we're actually computing how this value changes from its previous value. So assuming that all of the influence on this neuron is 0, this neuron keeps firing, or it keeps the same value that it had at the previous time step. Okay. Does this formula make sense to everyone now? Okay. Okay, so that's recurrent connections. Let's go back to backpropagation for just a minute, just to point out another challenge in artificial neural networks. Remember that in backpropagation, we were seeing what value arrives at the output layer. We were comparing the values at the output layer against the desired values. We were looking to see if any of those neurons were producing a non-zero error. And in our cartoon example here, this neuron is misbehaving. It's outputting a 1, but it should be outputting a 0. So we need to propagate backwards along the synapses that attach to it and change the weights of those synapses. Now that we've added recurrent connections, there's going to be a problem here. What's the problem? Remember the intuition of backpropagation. There's localized error. Only one neuron is misbehaving in this case. We want to go in with tweezers and only change synaptic weights locally to try and reduce error locally at that place. Did you have an idea?
Well, I was going to say that problems that the synapses, the recurrent one, is going to be acting on an error value.
Yes, so absolutely, right? So whatever error is occurring here, this synapse is going to be touched by backpropagation because we're going back along the synapses. We're also going to go backwards along this one and also backwards along this one. Then what? So in backpropagation, we keep going backwards. So in this case, we go backwards along this arrow. There's no more arrowheads arriving here, so we're done. We're also going to backpropagate along this synapse and change this weight a little bit. There's no arrowheads arriving here, so we stop. We go back along this arrowhead and change this weight a little bit. Now where do we go?
It's going to propagate through the whole network.
It's going to keep propagating, right? There are 3 arrowheads that are arriving here. So we also go backwards along this one, and along this one, and along this one. Backpropagation has now touched every synapse in our example here, right? So I've turned them red just to show that backpropagation is trying to change these error functions. Or sorry, it's trying to change these synaptic weights. So backpropagation doesn't work very well if you've got a lot of recurrent connections, right? Now we're not going in with tweezers and making a localized change. We've seen there's localized error, and we've come in with a sledgehammer and made changes everywhere, right? If you hit your computer with a sledgehammer, what's the chance you're going to make your computer run slightly faster? Not much, right? It's not going to work very well. This is not a very delicate operation. We're already influencing this output neuron, which was already doing the right thing, right? So very tricky to apply backpropagation in this case. There are improvements on the backpropagation algorithm that try and deal with this problem. But again, just to point out some of the challenges and open questions in artificial neural networks. Okay. Let's see. So again, just to connect this back to robotics, what we've been looking at in most of the examples here is supervised learning, right? So we know exactly what each of the output neurons should be doing for every possible input, or at least a lot of inputs, right? We know that output 1 should do this, output 2 should do this, and output M should do this when the inputs are this, this, and this. It's supervised, right? The supervision is coming from here. If we take the desired pattern and we compare it against the actual pattern produced by a neural network, we can localize where the problem is, and with backpropagation or some other algorithm, we've got a good chance of fixing things. So supervised learning is a lot easier than semi-supervised learning. So in semi-supervised learning, which is the situation that we're dealing with in this class, we have our robot, so now the input layer is a sensor layer. The output layer is a motor layer, and we want our robot to gallop. We don't know what the angle of every single motorized joint should be, right? All we know is at the end the robot traveled 6.3 meters. Actually, forget the galloping example. Let's just say we wanted the robot to travel as far as possible. Doesn't matter how it traveled, right? We don't know what the motor should actually be doing, so it's kind of semi-supervised. We can go back and tell the neural network, yes, you got the robot to travel quickly, or no, you caused the robot to move slowly, or not at all. Right? We don't have as much of a supervision here. So we can't apply backpropagation and localize where the problem is in the robot's neural network and fix just a few synaptic weights. So we set aside backpropagation and these other learning algorithms, and we turn instead to evolutionary algorithms, which work just fine in this situation. Right? An evolutionary algorithm is going to take the current neural network, make a copy of it, and when it makes a copy of that neural network, it's going to tweak some of the weights at random. If the new neural network gets the robot to do slightly better, we keep that neural network and throw away the original one, rinse and repeat, and around we go. Okay. Okay, that concludes our lecture on artificial neural networks. Again, this was a very shallow and broad treatment, but I hope you have an intuition for the basic building blocks that make up neural networks and how to train them. So far, so good? Okay, so let's carry on now. We're going to switch to the next tool of the trade, which is evolutionary algorithms. Evolutionary algorithms on the surface is a pretty intuitive idea. So as a computer scientist, you might look at nature and say, Mother Nature is running this algorithm called Darwinian selection, right? Descent with modification. We have a population of organisms. These organisms differ from one another. They look different and they act different. And some of that variation is because of genetic variation, right? The underlying DNA among these organisms is different. So the ones that don't survive long enough to produce offspring die off, and those that survive longer produce more offspring. And those new offspring are similar but not identical to the parents. And because they're genetically similar but not identical, they inherit some of this survival strategies of the parents. They also survive longer and produce more offspring. And if you iterate this biological algorithm for long enough, you get us and all the other great diversity you see on Earth. Right? So we're going to look at a lot of different evolutionary algorithms in this class. The one thing that unites all of them is that they're some sort of abstraction of this algorithm. Of course, biological evolution is exceedingly complicated. It's not really this this simple. Every evolutionary algorithm is an attempt to abstract away a lot of the messy details of evolution and boil it down to this basic idea of trial and error using a population. So in our case, we're going to have a population of genotypes. So we're going to use the term genotype to refer to biological DNA or to the data structure which specifies a solution to our problem. We have our genotypes here in our population. At the beginning, we're going to generate a population of random ones. We're going to then evaluate each of these individuals in the population, each one of these genotypes, one after the other. The ones that score low on our fitness function, whatever that fitness function is, are deleted. And the ones that scored high, we either produce copies of them or we take parts of individuals and combine them to create a new individual. What biological hack am I referring to? Combine genetic material from multiple individuals to produce a new one.
GMOs.
Maybe, yes. Maybe this is a GMO. I hadn't thought about it that way. That's a good point. Yes?
Organ donation?
Organ donation, kind of.
Gene splicing.
Gene splicing or in general sexual recombination, right? We're assuming we have two individuals in the population or maybe two robots. Maybe each of them has solved part of the problem but not the whole problem. Maybe these two individuals have solved different parts of the problem, and if we combine genetic material from both of them in the right way, we might bring together the best of both worlds and produce an individual that's superior to either parent, right? That's why sex evolved in nature in the first place. Okay, so again, that's the basic algorithm. There's a whole field of evolutionary computation. We're going to talk in this class about evolutionary robotics, which is basically taking an evolutionary algorithm or a genetic algorithm, combining it with a robot simulator, or maybe even robots in reality, and evolving not individuals in a population, but evolving robots in a population. And I'm doubtful I'll be able to play these videos for you in the slide deck, so let me see if I can do so from here. This is, again, just an example from a project from a while back. We evolved, in this case, our primate robot to perform brachiation, or a form of brachiation, which is just a fancy term for swinging from one handhold to the next. What can you tell me about this particular evolved solution to brachiation? So this robot has a neural network inside. Yep.
I mean, it understands it needs to counterbalance, I guess.
What do you mean by counterbalance?
When it's moving, it understands that it needs to shift its weight for the center of gravity.
Exactly. So what we're simulating down here is the battery pack for this robot. We did this work 15 years ago now, so battery technology wasn't that great. The battery was pretty heavy, so the robot is dragging this battery below it. But you'll notice that evolution here has exploited the fact that this is a complete agent. Remember our discussion about embodied cognition last week, right? It has to drag this weight along with it, but instead of fighting against it as an obstacle, instead, evolution has sculpted this neural network to exploit the weight of this battery, right? So it gets it to swing in a certain pattern that frees up the weight on the hand, and when the weight frees up on the hand, there's less friction and it's able to slide its hand forward, right? So we as bipeds exploit the fact that our legs swing when our foot leaves the ground. Our monkey robot here our evolution has discovered how to exploit the same thing. Okay. In this case, we were sufficiently interested in the solution. We built it in reality and could get the robot to do more or less the same thing. The physical robot to do more or less the same thing. Okay. So again, that's evolutionary robotics, combining an evolutionary algorithm with either physical or simulated robots. Okay, so let's talk now about evolutionary algorithms themselves. Let's set the robots aside again and talk a little bit about the theory underlying evolutionary algorithms. As we do, as we go along and talk about a few different evolutionary algorithms, we're going to use a particular metaphor which was introduced by Sewell Wright, a biologist back at the beginning of the 20th century. And the idea here is to think about the space of all possible solutions to your problem, or all possible organisms on Earth, and to think about biological evolution, or in our case an evolutionary algorithm, as a search algorithm. It's looking for organisms, or in our case, robots that achieve high fitness, that survive and produce offspring, or in our case, that exhibit behavior X. Okay, what is a fitness landscape? Well, imagine for the moment, to start with, that we have a piece of DNA or a data structure that has just a single gene in it. Let's imagine that we have a very simple robot, and that robot has one sensor neuron, one motor neuron, and a single synapse that's connecting the sensor to the motor. Let's assume that we're using the tanh function for our activation function, so there's no threshold that we need to evolve down here. We have a single weight. We have one number, and as we now know, if we change this number, we change how the robot is going to move in response to what it senses. Right? So we want evolution to try and tune this weight to produce whatever behavior we want. So let's imagine now that that weight becomes that one number in the genotype. It's the one thing that evolution is going to play with. If we do, we can now, on the horizontal axis, imagine an almost infinite number of points, and each point corresponds to a value of W. So when you actually get to the synapses project, I think the weights of the synapses range between -1 and +1. So imagine our horizontal axis here ranges between -1 and +1. We could then take each one of those values of the weight, drop it into the neural network, and simulate the robot and measure how far the robot moves, the fitness of the robot. We would then take that dot and plot the height of that dot as its fitness. So this would then produce, if we were to evaluate a whole bunch of these robots, it would produce this one-dimensional fitness landscape, right? We've got hills, we've got valleys. Where are we trying to get to in this case, in this cartoon example? The highest peak, right? And where is that here? If our horizontal axis is between -1 and +1, it's near the middle, right? It's near zero somehow. When you run your hill climber project, you're going to see exactly this in operation. You're going to actually be evolving just a single weight. And when you run your hill climber over and over again, which is one of the first search algorithms we're going to look at, it tends to converge to the same value of W over and over again. Okay. That works very nicely in this case, however. But you can see that there are places where we can get trapped here, right? So there are certain hills here which are lower than the overall peak. We've already mentioned this term before. The hills where something could get stuck, these are local optima. So if we just looked on this fitness landscape locally, let's say we just looked at values of W between -1 and -0.5, in this local neighborhood, this is the optimal value. It's a local optima, right? The mountain in the middle is our global optimum. In this case, there's just one optimum. That's where we're trying to get to. The tricky thing is for everything you're going to do in this class, you don't know what the fitness landscape looked like. If you did, there'd be no need to run a search algorithm, right? Set W to 0 and off you go, right? So what an evolutionary algorithm is doing, or any of these search operators, is moving about this space, this fitness landscape, and trying to find the peak, right? Every time that we change the genotype, which in this case is changing W, what happens to the point that we're at? We have a particular robot and we change W. Where does this point move, given this idea of a fitness landscape? Let's say we start with a robot that has a W of -1.
Moves up.
So in this case, moves up, but not very much, right? We then change the genotype. We change W. Maybe it changes from -1 to -0.9. Before we've even evaluated this robot, where has this point moved? It's moved horizontally, right? We were starting here with a value on the horizontal axis of W equals -1, and we changed that weight a little bit to W equals -0.9. So we've moved horizontally a little bit. Then we evaluate the robot and we know what the height of that point is. So you can think of these search algorithms as kind of dropping points in this hidden landscape, and then when we change the genotypes of those points, we're searching. Those points are moving about the space, and we're seeing whether those points move up or down. Okay, we mentioned the genotype. This is going to be the term that we use for storing genetic information, either DNA or some data structure that's storing information about our robot. The phenotype is what happens when we evaluate the genotype. What does the robot look like, or what does the robot do? So at the beginning of today's class, I showed you this sensor data generated by a robot. That sensor data is a part of the phenotype. It's what the robot did. This number is the genotype. The sensor data is the phenotype. Okay. So fitness landscapes are pretty easy to visualize if our genotype only has one number in it, one dimension. What happens if we then expand our robot? So now it has two sensors, and those two sensors attached to the single motor neuron. We now have two weights. So we now have a genotype which has two numbers in it. Right? Now we have the case in the bottom right here, where again we still have a horizontal surface. Right? And at each point in the space, each horizontal point in the space corresponds to a particular setting for W1 and W2, and we then evaluate that robot, and if it travels into the screen, the direction we want it to travel, then the point is up here. If it travels towards us out of the screen, that's bad. It gets a negative fitness, and the point lies below the horizon here. So again, now in 3 dimensions, we can see that our fitness landscape also has a number of local optima, places where it can get stuck, and one global optimum. Let's imagine that we expand our robot again. So now it's got 3 sensors and 3 weights. What does that landscape look like? Why have I not drawn that one for you?
Too many dimensions.
Too many dimensions, right? So now we're going to have a fitness landscape that exists in 4 dimensions. 3 of the horizontal dimensions correspond to the genotype, and the vertical axis, the 4th dimension, always indicates the fitness, right? Okay, so human beings in our DNA, they're still trying to figure it out, but it looks like we have about 30,000 genes. What does the fitness landscape for humans look like?
30,000 dimensions.
Not quite 30,000. 30,001, right? I don't know how you compute the fitness of a human being, but there you go, right? So the fitness landscape from now on is going to be just sort of a thought experiment. We're not going to be actually able to visualize it very well, but you get the basic idea, right? We've got this surface, and we're looking on this surface for the highest point. Okay, so let's go back to our cartoon example of a genotype that just has one gene or one value in it. And let's start with the simplest and weakest of all search algorithms, which is the hill climber. So I just added this project on the end of our project series, so you can go and have a look at that. How does this work? I'm going to use this cartoon here, which is sort of, again, a cartoon of Darwinian evolution here. This isn't really evolution because we don't have a population in this case. In this case, or we have a population, if you like, of 1. We have one individual, and I apologize here, the genome obviously has more than one gene in it. Imagine this is a vector with just one element in it. let's start with a parent that has just one randomly selected value. Let's imagine that value is out here. We compute the fitness of that parent, and it's here. Okay. We then copy the genotype, and when we copy the genotype, we introduce a slight mistake. We randomly perturb the value. What biological hack are we simulating in this case? So this isn't sexual recombination. We're not combining genetic material from two parents. Mutation, right? So one parent, we produce a clone, and then something goes wrong during that copying process, so we have a mutant from the parent. So we've mutated this value, which means, again, the child has moved horizontally somewhere in the fitness space. We then evaluate the fitness of this child, and you see in this case the child is not as high as the parent. What does that mean? Throw it out, right? The fitness of the child is less than the parent. Like biological evolution, evolutionary computation is pretty cruel. Throw away the child, try again, right? So now maybe the parent produces another child. Maybe that child happens to land here. What happens in the case when the child's fitness is higher than the parent's? Throw the parent away, keep the child. The child becomes the new parent. Repeat, repeat, repeat. In this cartoon example, what happens? Sorry?
Gets to the top eventually.
Gets to the top of what? Which one?
The second one,
Does it get here?
hopefully.
Hopefully, right? This is what we're always hoping for. What's more likely to happen? It's going to get stuck on this local optimum, right? If I'm mutating or making a slight change to the parent, the child is always usually nearby the parent. And nearby means basically the distance, if you like, between the genome, the genotypes of these two individuals. Usually pretty close to one another. So in essence, the hill climber does exactly what its name implies. Wherever the hill climber starts, it starts walking up the hill that it's standing on, right? What happens when the parent gets up here? It gets stuck, right? Most of the children that it's producing are nearby. They're worse than the parent. They're thrown away. The hill climber might get lucky, and a particular mutation might be big enough to actually that wouldn't do it, right? Even if the child lands there, that child will die. It's got to go at least this far to produce a child that is more fit than the parent and is now on the slope of the global optimum, right? Tricky. Okay, so again, pretty simple algorithm as you can imagine. I think it takes about 8 lines of Python code to implement this when you get to this project. It's not that difficult to implement, but it's a weak learner or a weak search algorithm because it tends to get stuck on a local optima. All of the evolutionary algorithms we're going to look at in this class are more complicated than the hill climber, and we're introducing those complications because we want to increase the probability that we can escape a local optima and eventually, given enough computation, find the global optimum. Okay, we got 2 minutes left, so let's move on to the next algorithm, which is the parallel hill climber. What's the easiest way to make sure you don't get stuck? Well, don't start from one position, right? So now we've moved into the class of population-based search algorithms. So now we generate n random parents. And each of the n parents is a hill climber, right? It produces its own child. And if that child is more fit than that parent, away we go. Okay, how do we do in this cartoon example here? Do we do better than the individual hill climber?
Technically?
In this case, not really, if you increase the population, right?
Exactly. So here I've increased the population size to 2, and I still get stuck, right? I got unlucky. The 2 parents happened to fall on the 2 local optima. So I ratcheted it up to 3 or 10 or 100 or 1,000, and I'm hoping that I dropped at least one of the parents on the slopes of the global optimum in this case. In this one-dimensional case, it's not going to take many parents. What happens if instead of 1 weight, I have 20 weights. So we're back to now a 21-dimensional fitness landscape. Not an easy thing to wrap your mind around. What do you think the chances are now of landing on the slope of the global optimum in that case? It's much, much less. Much less. There is a curse in machine learning, including evolutionary algorithms, called the curse of dimensionality. As the dimension of your problem goes up, curse of dimensionality, as the dimensionality of your problem goes up, it gets harder to solve your problem, and it goes up it becomes much worse than you think it does. You're not 20 times less likely to land on a global optimum when you go to a 21-dimensional fitness landscape than a 1. I don't know what it is, but it's much worse than 20. Okay, and you are going to be evolving robots that have dozens of weights, so you are definitely going to get your full measure of the curse of dimensionality in this class. Okay, we'll leave it on that pessimistic note today. You have a quiz due tonight. Undergrads get started on assignment 3. Grads, you're working on 5 and 6. Thank you.